In the year 350 BC, the famous Greek philosopher Aristotle said that our Earth is a stationary object in this solar system, and that all the planets, including the Sun, revolve around our Earth. Then in 1543, when Nicolaus Copernicus presented his detailed theory of the universe, many got confirmation of what the real planetary motion is and how things work in the solar system. However, while reading about this, a question arose in our minds. Can humans really transport the sun like an object, or at least move it from one place to another? And the things we learned will truly blow your mind. So hello friends, I am Astro Stellar Tech Universe, and let's start another new episode. How to move the sun. First, it's important to understand why there is a need to move the sun. There are two big reasons for this. When we need to relocate at the interstellar level, we would be able to transport our primary energy source, the sun, with us. The second reason, which directly resonates with the red giant, is a bit theoretical. Suppose when our sun is in the red giant phase, it will keep expanding, and its Goldilocks zone will also extend. Eventually, at some point, our Earth will move out of the sun's habitable zone. In such a situation, if we can move the sun away while keeping Earth in its place, we can extend the habitability of our planet for at least 10 to 20 million years. Moreover, in moving the sun from one place to another, we might discover a better way to harness its energy, fulfilling our extensive energy needs. All these things are achieved through stellar engines. A stellar engine is a kind of cosmic megastructure that can either harness the sun's energy or provide thrust using that energy to move the sun or, if needed, the entire solar system to another place or control their motion. By 2024, several models of stellar engines have been proposed. But is it really possible? Friends, theoretically yes, but is it practically possible? Let's discuss it one by one. Friends, the concept of the first thrusting stellar engine in human history was given by one of the craziest astronomers, Fritz Zwicky. For those who don't know why he was so great, let me tell you that today's dark matter that makes you so curious, and the neutron stars that help us technologically, were first proposed by him. Similarly, humanity's first stellar engine idea was also given by him, which was a bit different from those proposed later. He proposed that we could launch a large particle accelerator into space that would shoot particles at near light speed towards the sun. Now, because these particles traveling at near light speed would have no shortage of kinetic energy, as soon as they impact the sun's surface, these particles would initiate high-energy fusion reactions, creating such a powerful and energetic solar jet that it would displace the sun from its current position. In this way, our sun would use its own matter as a propellant after the ignition impact, moving in the opposite direction of the particles we shoot. As Newton's second law suggests, for every action, there is an equal and opposite reaction. However, Zwicky was never given the status of an astrophysicist from an astronomer because he never went into the maths of history. He would just propose ideas and move on. But what can we do? We took the responsibility of this math and thought of calculating how much energy we would need. So friends, let's do the most basic calculation. Einstein gave the formula E equals sine mc2. This means to calculate the required energy, we need to multiply the mass of particles by the square of the speed of light. So for instance, if we take a proton as the particle, its mass is 1.67 times 10 to the power of negative 27 kilograms. But we can't even use the normal proton value here because according to the Lorentz factor, the mass of a particle also increases with relativistic mass as its speed approaches the speed of light. Now if we assume the speed of the particle to be 99.99% of light, then its Lorentz factor comes out to be 70.71. In the relativity equation, we need to use the effective mass of the proton, which is the Lorentz factor multiplied by the rest mass of the proton. Multiplying these, we get the value of 1.18 times 10 to the power of negative 25 kilograms, and when we multiply this by C2, we get the value of 3.54 times 10 to the power of negative 9 joules. This much energy is required to accelerate just one proton, which is not much. But if you consider that we need to move a massive celestial object like the sun, we would need a continuous supply of energy for these protons. Now even inside a basketball, there are approximately 1.05 times 10 to the power of 30 protons, and since we need to energize even more protons, this small energy requirement can reach trillions of joules on a massive scale. That too for a single push, which is currently beyond our capabilities until we learn to harness the energy of celestial objects. About 26 years after Zwicky, in 1987, Russian physicist Leonid Kurnos proposed a paper titled Possibility of Controlling Solar System Motion in the Galaxy, in which he proposed a mirror structure that would work as a thruster by reflecting sunlight back towards the sun. The photons released by the sun give it a very unnoticeable push in the opposite direction of the light emission. But since these photons are emitted from every corner of the sun, all the rays cancel out each other's push momentum, keeping our sun stationary. This is where the shadow void comes in. He said, what if we focus all the sun's rays in only one direction? In such a case, the light momentum, which was keeping the sun in one place, would start pushing it in the opposite direction. He said that if we set up very large concave mirrors on one side of the sun, we would curve the light falling on that part of the sun so that it reflects back onto that part. This would increase the radiation pressure on that part, and the rays emitted from that part would start pushing the sun in the opposite direction. And we can slowly move this whole system anywhere in the galaxy as per our needs. Now imagine after firing this engine at the sun, how the sun would very slowly move from its place. You would see that this movement is so slow that no one can see it without specialized equipment. But after 1 million years, this speed can be 20 meters per second. And after 1 billion years, this speed can be 20 kilometers per second. And during this time, we can travel 1/3 of the Milky Way's width. Now our question is, should we move the sun, or is it a ridiculous idea? Do share your thoughts in the comments section below. If you like the video, do like it and share it with your friends. And subscribe to the channel and turn on the notification bell, so that you get updates on such videos first. See you in the next episode. Until then, bye and Jai Hind.